Okay, hi, do I have a voice? Is everything? Yes. Okay, so hi, everybody. I hope you're doing well. Uh, so, tomorrow and there will be a quiz. You should have received an email saying what is covered. This so the first quiz will be about section 1 and 2 from chapter 15, and then the rest. Uh, okay, so last week I did not uh, finish what I wanted to finish, and unfortunately that section uh, is a bit long, so I have to cut off some material in the hope that you will uh, learn some of it in the exercises. Okay, but basically the what I wanted to cover is applications of. Okay, so let me see. So the plan for this week is to finish. Um, finish the applications, right? So yeah, so if you didn't notice, my notes are online. Uh, I did scan them, and they are quite clear and well written, uh, to the best of my knowledge, of course. So if you want to take a look and just see, if you don't want to read thousands of pages from the book, that might be a good place. Uh, let's find where is my. So yeah, we would like to finish applications of double integrals, right? That I will do very quickly, and then I would like to start talking about surface area, and then change the variables. Okay, so that's for today. Hopefully I can get through this. And then we'll do the others. Okay. Um, so as I said, I will talk about some applications of double integrals, but as you can see, they are all the same. It's just the physical interpretation is not the same thing, but the calculations are the same. Okay, so okay. This one is not really working well. Applications of double integrals. I don't know if you guys hear the birds singing. Unfortunately, I can't do anything about that. Okay. Uh, all right. So let's do first density of and mass. Okay. So the idea is again the same. If you have a certain kind of a plate, like for, some form, some object or a plate, or you know, made of some material, and the density, right? So let's call this one some form D, right? Some object D, and the density of this object depends on a function. Of course, if for example, what is easy? The easy, when it's easy, it's like uh, when you have an object and the density is, let's say, 2 gram for, per I don't know, meter squared. So you just have to calculate the area and then multiply by the area. It gives you the total mass, right? That's the obvious way to do. But the problem comes when this density here is not uniform. Like, for example, if you take a small little uh, um, box or little piece of this object, density is not going to be the same as here. Like, for example, here's going to be 2 gram per unit square, and here's going to be 3. And it's going to be a function of, right? So the density will be some function of x and y, right? So this is x and y. So it's going to be a kind of, oh, x. So it's going to be a function of x and y. And it's going to be kind of instantaneous change of the density. So what you do here you do the same thing as we've been doing, like, and we'll keep doing the same thing. We divide and we take the limit. So what you do is you divide into small rectangles, right? And then you take, for example, this rectangle, right? And then take a point inside, right? Call it x I j y I j star, right? Any point you can choose. And then what you do is what is the mass of this small rectangle? So the mass, right? We call this one R I j. The mass of R I j is approximately, right? Not really. I mean, because the density is a function of a point, not, so it approximately, because if the density is continuous and the rectangle is very small, it's going to be like, right? If you have a function that is continuous, right? When you take a very small rectangle, it's going to be the same thing around this. Um, it's going to be almost the same value when you take a very small neighborhood. So what you do is you just you take the density of this point here, y I j, sorry, And then you multiply by the area of the rectangle, which you're going to call it delta A, right? Delta X, delta Y. Because here we assume that we divide the rectangle uniformly, right? We just choose some fixed width here in X, and then we choose some fixed width here, delta Y. And then you multiply. And then what you do, so the total mass is the sum our all, sorry, that's a big, this is a big sigma. It's the sum from I to N and from J equal to 1 to M of all these small rectangles, right? Delta I, delta A. And if you remember, and then you take the limit, remember you have to take the limit because, again, I'm gonna just recall this one. The smaller all the rectangles, the better you're gonna have an approximation of these smaller rectangles because the function is always assumed to be continuous, right? And then when you take the limit, if it's continuous, the limit will always exist because we always assume these regions to be bounded. And this will be just, if you remember, you go back to the definition of an integral. For double integrals, this is the definition of the function rho xy dA over the region D. So that's the total S. So right, that's the idea. And the same thing, you can apply the same idea, only n goes to infinity. Oh, sorry, yeah, both of them. Because you want to take smaller rectangle, because if you only take n equal to infinity, then you're gonna have some fixed width here. So you're getting like very narrow rectangles here, but it's not a better approximation. You have to take n and m, both of them, right? So that they can, all of these rectangles, they're gonna be some small point because they did this because by the end, your region will look like this, very small points all around, right? That's what you want. They're gonna be very small, right? And then, so the idea is actually the same if you want to apply it to any kind of other physical phenomenon. Like for example, if you have a kind of wire and you have some electrons moving, right? Right, going on this direction. And then you're gonna have some, the density of these electrons, right? Some, for example, the charge Q will be some function of X and Y, right? So this tells you how many electrons you have per unit square, right? So what is the total charge of this box or this rectangle? Well, same thing. You just have to integrate. So the total charge will be the same thing. It's the same idea. You divide and then you multiply. One case was the mass. This one is the charge. It has the number of electrons per square. So that's exactly the same thing. It's gonna be some Q will be just the integral of, let's call it sigma here, right? Sigma is a function of, like, is the number of electrons per unit square. So you just have to integrate sigma dA over the rectangle D. And then if you want to, if you're going to compute and in all of this depends on the time. For example, for some fixed time, this is just for your information. If this all depends on the time, like for a fixed time, then it's going to be a three variable function. We are not covering this, but we're going to cover this the next week. But if this is a 3 variable function, then you just fix t, right? Then you integrate with respect to dx and dy. So this is going to be a function of t. And then if you want to look at uh, how it's called, the what is called I, the intensity of the, like the change. That's exactly the change, right? You just have to compute this, right? So that's gonna be the how many ampere you have. But this is not. This is just for your information. It's not covered. It's not covered by, right. We will do 3 variable next week. Okay. So the same thing. Okay. So let me do moments and centers of mass, and we'll do an example, and then I will tell you a little bit about probability. But probability, there is an exercise about probability for this week. Pretty long exercise, but it's the same idea. Okay, let me do the center of mass. So this is actually a cool thing, moments. This is one of the good applications of double integrals in physics, because, for example, if you have some kind of very unusual object, and this happens when you try to craft something, and you make it, for example, you want to fly something, right? A plane or something. So what you want to do is you want to find the center of mass. That is the point where, if you this is the point where so we want to find a point where if you support this object on some horizontal, on some balance, and you do it like on this point here exactly, then it's gonna balance horizontally, right? So that's the you can, I mean, for a straight, for example, if you have a straight object, right, and with the kind of different mass all along the line, you can do it pretty much easily, right? But the simplest case would be, for example, if you have just like one ball here and a smaller ball here, right? And you want to find that's a very simple exercise in physics. So where is the point here, such that it can balance if you hang it on this point, right? That's a very simple application. So that's the simple one. It has to do with moments of mass. You have to do like the force here and the force here, and right, and you have to find the point where all of this will balance. And right, so the moment will be something like x, and then here it's gonna be y, right? For example, this is L, then L minus X, and then you have to solve the equation L minus X times the force here. You have a force 1, and then I have a force 2. And this is have like certain mass M, this has certain mass M, and then you have to find X. You have just to solve L minus X times M times G, like the force is M times G, equal to X times. So where is X, such that this is true, and it's just a linear equation, you have to solve it. Now, how we do this for, how can you do this? This is not an easy exercise if you were to do this for a two-dimensional object here. So here comes the double integral, right? double integral. So here I'm gonna give you just the answer. Uh, I wish I could speak about this more, but the time is a bit limited. So for example, here, this is x, this is y. So what we define is, it is called the, let me see, yeah. So again, we're gonna just divide this thing into small rectangles, okay? Okay, and the same thing. We take a rectangle, we take a random point inside, well, admit, okay? And, right? So for this point, there will be a distance from the x-axis, we call it, so this is x, I, j star, and this is y, I, j star, and this will be right, and then the distance here will be x, right? Um, right. So when we define, so let me, what's the best way to say this? So consider the rectangle. This is the rectangle R, I, J. Okay. So this rectangle looks like a point. That's the idea. When N and M are really, really big, it looks like a point. So we're really dealing with a situation here where it's exactly the one I gave you in the beginning. It's like you have a little ball here, like a right, and you have this thing here, and you have this distance here, right? Um, yeah. So what you do is you take the mass and you multiply by the distance, right? Because g is almost the same. Because normally what you would do is, if you really want to go to the physics, you want to take the force applied on m, this small mass m, right, times the distance here. But we're just gonna give you the answer here. So what we do is we take m, we take the mass m, and we multiply by the distance from the x-axis, right? So, right? So the moment, so the moment is a definition. If you have a mass and you have this, you have an axis, the moment of a mass with respect to this axis is the mass itself times how far is the mass from the axis. So the moment of uh, of the rectangle Rij, right? This is the rectangle Rij, right? It has a mass m. Is m times, how far is it? So it's times the distance from the x-axis, which is equal to now what is the mass of m? Remember, we have a density here. Density is always given, right? Is the density applied to the point right times delta x delta y, but to not confuse you, this is just delta a, right? This is, all of them, they have the same. It's delta x delta a. This is delta a. This is delta a. All of them, they have small areas delta a, right? So this is the total mass times y. Okay, so the total the total moment is the sum. Right? Okay. And then again, if you remember, what is this? This is just the integral of the function rho x y. And now you have to multiply by y dA times the region B. So that's the total moments with respect to x, right? It's with respect to x because it will balance will balance in a direction. If you stay on, like, okay, let me just finish. If you when you okay, let me just compute mx right now. Okay, now we do the same thing, like similarly. We obtain, so we do the same thing, but now with respect to the y distance from the to the y axis. We obtain the total. No, did I start recording? Please tell me. Okay, it's recording. We obtain that the total moment. Oh, did I say that here? The total moment. Sorry. With respect to the x-axis is total moment with respect to the y-axis or about the axis is my okay. Okay, and then we define the center of mass of D as mx divided by the mass y, my divided by the mass, where m is the total sorry, it's D, where m is the total mass, is the total mass of D. So as I said, the physical interpretation is this point here. When you find this x and this y, right, it's gonna be something, right? It's gonna be something like this is the region, and then you're gonna find x bar and y bar, x bar and y bar, and then it's gonna balance fully when you support it on when you support this region B on this point here, right? So that's the physical so that's the physical interpretation of it. Okay, okay. So that's a very useful thing to know. Uh, if you want to know more about why is this true, then maybe you can ask me during the break or. But let me move right now because we are running a bit of time and would like to finish. Okay, let me just do an example and we'll move to very quickly on probably. Okay, so I see someone who wants to see this page. Have you done? Any questions? Okay, let me do a quick example. Very, very simple example. It's just you have this triangular area region, right? And here we have 1, 0, and here we have 0, 2, and then we have yeah. I was just gonna, like, for example, if you have some function here, O, X, Y, right? So what will be the total mass? The total mass would be would be this is R, it would be the integral over R of this function here, the A, okay, which would be the integral from 0 to 2 minus 2x, because this is the line y equal to 2 minus 2x. And then from 0 to 1 of this function here, dy dx. Mx would be same thing, the integral over R of O x y y dA, which would be exactly the same thing. You just take this function here, integrate as you do, O X Y D Y dy dx 0 to 2 minus x 0 1, and then my did I use the same notations here? Okay, so I don't want to confuse you. Well, it's just a notation. Let me just check. Sometimes they do confuse people from other books. Okay. Let me see. Okay. Mx is the integral. No. Can you check the book again? I don't know which book you're using, but that's the same notations they're using. Mx is the integral. No.
Wait, I'm sorry, I can't see the screen anymore.
Yeah, I know. It's fine. Okay. No, I don't know which book you're using, but that's the exact same notations I'm using from the book. So yeah, all right. So I don't know who sent me that message, but that's exactly the same notation. So let's continue on this. Yeah, sorry if there's any discrepancy between that can happen, but hopefully not that often. But the concepts is the same. The only thing that can be confusing is the notation. Okay, so my would be the same thing. So I will not do an explicit example. This is just to right, and then you can just plug in any function you want. Now you can choose any functions, O, X, Y, and compute this, compute this, compute this, compute these three quantities, and then by the end of the day, you just have to divide. Mx will be this divided by m, and then y bar will be my divided by m, and that's the answer. So, for example, and then it's always given. So it's again like sometimes like okay, they give it to you, or they're gonna give an explicit sentence that says okay, varies as a square the distance from the origin or something like that. Like for example, someone asked the question, what does it mean? Right? There is an example of this from the exercise. So I'm gonna skip the moment of inertia because it's gonna take us another time, but it's exactly the same concept. And I'll make sure that if it happens that you need that, you need, or you can read the notes. It's exactly the same thing. It's just instead of static objects, we'll have to rotate objects around axis, and we will have to find the points where, uh, yeah. Okay. Um, yeah. Okay. Probability. Uh, okay. Probability. I will just give an explanation without any example. Okay. Probability. Okay. Okay. So probability is the so if you have two random variables, if you have two random variables, x and y, right? Right? Continuous, that are continuous, that are continuous. Meaning that sometimes you will have oh yeah, yeah, of course. Sorry, thank you. Yeah, same thing here. Sometimes you'll have some random, thank you so much. Sometimes you will have some phenomenon that has two variables that are random, for example, and that are continuous. For example, midterm grade, right? That, it's not that continuous, but, or for example, the waiting time in a queue inside some store, that is going to be a random variable that, for example, in 2 minutes, 4 minutes, right, depending on the customer, and that is going to be a random variable x, and then you're going to have another variable, which is just, we're going to have another variable, for example, the time that another person is waiting. Like if you take two customers, and then you see how long this customer is waiting and how long this other person is waiting. This is going to be a two variables, and it's going to be random. It's going to be continuous. It's not like the midterm grade of random students. That is going to be kind of continuous, and this is, you don't need integrals for this kind of probability problems, but for this kind of continuous problems, you need integrals. And in general, how we do these things is we define the joint density function. Density function of x and y, right? It is a function. It is a function of two variables, right? Called f x y, and I'm going to explain this use a diagram to explain this. So, for example, if you have this function, if I give you this function, right? Your job is not to find this function. Your job is just to understand. In probability classes, you have to find these functions. But when I give you this function, and suppose I give you a domain, right? For example, this is the time, and this is well, this is the variable x, and this is the variable y. So, and then I ask you, what is the probability of uh, having the it's, we in general in probability we talk about events. So consider the event. Consider the event. This is the domain. Consider the event. If you pick two customers, and what is the probability that x and y will be inside this domain? Right. This is an event. If you pick two customers, you ask the first one and the second one, how long did you wait? And the second one, how long did you wait? What is the probability that the waiting time x of the first and the second will be somewhere here, right? It can be, I don't know, like this is 2 and 3, or right? So what is the probability of this event? So the probability event, uh, the probability of this event is given by probability xy to be inside D is just the integral of x, y, dA, d, right? Yeah, and they need to be independent. Right. No, they don't need to be independent, right? Again, okay. So I'm moving a bit faster here because I don't want to make you um, okay. So this is just a definition. I give you a function of two variables, and I tell you it's a probability function of x and y. So by definition, it means that if I ask you what is the probability that I will find x and y inside D, you just integrate this function here. And this function has the following property. It always positive, and it has the following also normalization condition. If you integrate over all R2, right, it's 1. This means that something will happen. I mean, if you pick two customers and you ask them what, I mean, it's gonna be something. X, Y will be something. So the probability of that's the meaning of that. Other than this, I don't think that you need to find anything. If the two events are independent, meaning that the first customer has no idea or has nothing to do with the second customer, or the fact that the first customer got a service does not affect the second one. You know, if there is no correlation between the first customer and the second customer, then they called independent events. If X and Y are independent, then fx y will be just the product of these two functions, where this one is the I guess you know that. I guess you have covered this somewhere. As the probability density function of a single variable, like you, right? The probability density of x. Same thing. Equal. Sorry. Is everyone all right? Is this a bit fast? Or yeah, in the exercises you will do some very explicit examples. But don't worry, they will ask you exactly what you need to know and what you need to compute. I don't understand this comment. Equal, 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 equal. Sorry. Can you be more explicit next time? All right. I think we'll take a break here, and we'll try my best to cover surface areas and change of variables. Okay, we'll be back at 11:12. Is it? Yeah, 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 yeah. So again, the goal is not to make you learn probability here. The goal is to make you aware that these are the applications and this is where we're gonna see this. Of course, if you take a class in probability, it's gonna be a bit more than this. It's gonna be, you have to find the x and the meaning of all of that. But the goal is just to make you understand that these double integrals, we use them in real life. And I have used this in my personal life. This is just an anecdote. Uh, I used to, um, uh, what is called scratch building airplanes. You build small airplanes from foam board, and you have to build it like on your own, meaning that you have to uh, find all the places where the battery will uh, be balanced on all of that. And for that, you have to find the center of mass, because otherwise it's not going to fly well. So these are really real applications of double integrals. And if you have a it's not, I mean, you need a computer, of course, if you are doing this for real life, because a small airplane, depending on the model you have to compute it, like you have to break it down into rectangles and triangles and find each center of mass, and you need double integrals for this, and probability also. I guess people, they use this every time. So the goal is not to make you learn any physics or probability, but the goal is to make you aware that these are worth to learn. That's the thing. That's the goal of the class, I guess. Okay, we'll be back at 11:12.
I'm sorry, like if we have questions, can we book an office hour?
Office hours?
Yeah.
Um, Normally,
Like because there's no like for the mass center they don't have they don't have like for 235.
you're talking about Math Ed Center?
Yeah, because they if we're having questions like I can't go to math center to ask them because they don't offer their 235.
Yeah. So I haven't received any kind of directive about that, because I guess the TAs. What do you know if they are offering any kind of office hours?
Like for last term, and it's like from this is a second term, right? I mean like for
Yeah,
last they offer like office hour, like I can book an office hour with the professor, but I'm
yeah,
not sure for
yeah. So what I say in the workers is we can have an office hour. You have to send me an email because I haven't received any directive as to, because normally we would give fixed office hours each week.
Okay, thanks.
It appears that no one is doing that, and I am. So what I said is to be assigned, which means that you have to send me an email, and we'll fix an appointment, and we'll answer all your questions. But be aware that there are also TAs that they do have office hours too.
Okay, thank you.
So if you need something, just send me an email, and I can log in into Zoom and answer your question.
Okay, thank you.
Okay. So I'm gonna allow people to speak, but as soon as this is gonna be a bit uncomfortable and people will be speaking at the same time, I will just have to cut it off and not allow people to speak. I hate do. Yeah, some people are. Okay, so hello everyone. Hello back. Um, okay, let me start the new section. Uh, that will be section 15.5 and 15.9, but only two dimensions. Of course, the surface areas are in three-dimensional things, but objects, but okay, surface areas. Let me change this. Okay, so far you know how to compute the volume of function, right? So if you give you a function, okay, if you give you a function, right? This is z. Okay, so I give you a function. You know how to compute the volume of this function? Trying to be a bit. Sorry about that. Okay, okay, it's fine. To compute the volume of this function here, okay? How about the surface of this function here? So that can be also be done using double integrals, and the purpose of this section is to show you why the formula works and to do some exercises, some examples, right? Uh, so it's not going to be a proof. It's going to be why it works. Okay, so let's suppose I have a function, positive function, like suppose, right? The reason why you suppose it's positive is we don't want to deal with anything that will just make our life a bit complicated and how to deal with z negative and all of that. Okay, and we have a rectangle here. We have a region. We'll start with a rectangle, just as we did with integration under a function to compute the volume above any rectangle. So we're going to have a rectangle here, and we would like to compute the surface area that is bounded by these four planes, right? Like if you take a surface area, you take these four planes, you have to, and then you see the region of the surface that is bounded by these four planes. What is the surface area of this here, right? So this is the surface area we're looking for, right? Um, so you might guess that we're gonna do exactly the same thing again. Divide into small rectangles and see what we can do. Okay, so let's divide by small rectangles. Right? So we divide this into small rectangles. Why is it that it's doing this? Okay, divide by small rectangles. Okay, and we'll take this rectangle here and call it the rectangle R I J. Okay, and then you take the image of the four corners. Okay. Okay, so this will be some rectangle, some curved rectangle, I would say, right? Okay. Okay. Uh, we'll call this one here delta S I J, and we'll call this point the point P, I, J, right? It's the image of this corner here, okay? So, and this rectangle has area with area, delta X, delta Y equal to delta A, okay? And here, P, I, J will be equal to the point X, I, J, right? Because I don't want to make the diagram a bit more saturated, but uh, this is the point Xij. This is the point Xij, right? We divide this into X, wait, sorry. This is the point Xyj, sorry. Right? So we divide this into small rectangles, x1, x2, x3, x4, x5, and then y1, y2, y2. And then each time you choose a point here, you call it xi, yj. Okay. So fact is, if this function is continuous near the point P, I, J, the tangent plane will approximate the function f x y, right? This is exact similar thing that when you have a function and you have a tangent line around the point, right? What will happen is if you are really, really close to the point, they are the same, right? They are the same. They are the same. The line and the curve will be the same. Well, that's the exact same thing when you have a two-dimensional function, right? When you have a two-dimensional function, you have a curve, kind of curves, right? And then you have the tangent plane, right? You have the tangent plane, right? Well, near the point, they're gonna be the same thing. The, the error you're gonna make, of course, because you're gonna move a bit far from the point, gonna be a bit more, you're gonna make a bit more difference when you evaluate on the plane instead of on the surface. But near the point here, like around the point, it's gonna be the same thing, approximately. Uh, so, so if you stay really around the point, this plane and the surface, they're gonna look the same, right? So instead of this, I'm gonna just change the diagram. So if you are really, really close to the point, they're gonna look really the same, like this, something like that. Let me just change the color, maybe it's gonna help. Right, they're gonna look really the same. Right? And then this is gonna be some line.
Okay, so this is the tangent plane. This is delta S, right? This is the very delta Sij, and this is the plane. We're gonna call this part of the plane delta T Ij. What is this? So is this is exactly, you take the tangent plane and around, like, you have to understand that each point of the surface has an image on the plane itself. So this is the point on the surface. So that's the exact value of fx. For example, this is the point P ij, right? And this is some other point on the surface. So the image of this point, it'll be some image of some x and y. They can be approximated by the image on the plane, right? So this is the real value. So this is the real value, and this is the approximated value. But but again, as I stay around the point Pij, it's they are actually the same. The plane and the surface are the same. So so yeah, so if you want to approximate the surface delta Sij, so what is the surface area? So the surface area is the sum of all these small Sij's, right? But if all of these, they are approximated by these rectangles, delta Tij's, so the surface area, so I'm not gonna write everything here, I'm explaining a lot. But if you wanna read or miss something, that you just read my notes. I will upload them. It contains a lot of well, a lot of it. If you want really full explanations, then read the book. If you wanna just straight to the explanation, then just read my notes. Um, uh, a AS. So the surface area will be the sum of all of these, right? Well, let me first do it. So first we take the sum of all of these delta Sij's, right? But then as I said, all of these small delta Sij's, they can be approximated by this very small rectangle that lies just above it. So it is the sum of all of these delta Si's, which are, as I said, just these areas here, right? Right? Okay. Then you have to take the sum, because you are doing this only for one. So you have to take the sum, right? And you have to do it for every kind of rectangle here, right? And then as you're gonna take the rectangles smaller and smaller, these approximations here, they're gonna be better with this rectangle, and then you will have better, right? So this is exactly the same thing as you take a curve and you start doing this, right? That's gonna be an approximation of the length. Then what you do is you subdivide this thing here into two things, two lines, and then, right? And then you do this, right? And then as you keep doing this, you're gonna have a very approximation of the curve, right? And then as you keep doing it, you're gonna have kind of stick all of this on the curve, and it's gonna give you the real length. So the equivalent of the length on 2D is the surface area, so that's exactly what we're doing here, but just two-dimensional. So this kind of, it's hard to, I don't have the skills to do this, to draw this, but it's kind of 2D with a lot of small little rectangles sticking to the surface area. So that's exactly what you're doing here. So when you take the limit, then that's exactly what it, okay, that's a good formula, but it has not, but it gives nothing, right? It's a conceptual formula. But what we do right now is we're gonna give more details about this formula. Okay, so now we're gonna be a bit more explicit, right? We have our rectangle, okay? We have our okay. It's not the best. Okay. B, then A. Okay, so this is the point P, A, J. Okay, and this is the rectangle delta T, A, G. Right, so this is the, so this is a bit different. But do not, these are not the exact same layout, but so we have the rectangle delta Tij, and we would like to, so we have our point here, okay? And then this is gonna be delta x, and this will be some delta y, okay? And the area will be, because when we move in the direction of x, delta x, when we, right? Because what we did is exactly, we start from point Pij, and we move in the direction of x, along the direction of x, with an increment of delta x. So then we landed on this point here, right? And then we did the same thing on y, right? And then we landed on this point, then, right? And then we want, this is 15.5, I think, 15.5. Yeah, so then we landed on these different points when we moved away from Pij's, right? And now we would like to compute the area of this rectangle, okay? Now, remember, recall that this is x, this is y, and this is z, right? So when we move on the direction of x, we fixed y. So it gave us so here's a kind of directional derivative with respect to the direction x. So here you have to remember what you did in the first term is I give you a surface and I ask you to give me the two vectors that give you the tangent plane. Remember this, right? That you should have done this before. It's I give you a surface, I give you a point, then I ask you what is the tangent plane at this point. So that's exactly what you're doing. I give you a surface, I give you the point Pij. What is the tangent plane at the point Pij? Well, the way you do this is you have to remember that I'm not gonna reprove it, but the way we do it is this. So you say recall that this vector here, recall that the tangent plane at the point Pij is given by the two vectors, right? Because remember, a plane is determined by two vectors. The two vectors UA, right? This is now you will understand why I call it UA and not A. It's wait, I'm just gonna remember. This is X, Y, F, X, Y, right? So when you fixed Y, it gives you a curve. So we want to take the directional derivative is the dx dx, right? At the point Pij. Remember this. And this is 1, 0, fx evaluated at the point xi, y, j, right? This is the point xi, y, j, right? Well, maybe it's better to, yeah. So, okay. Now, why did I call it UA? It's because it's not going to give you the vector A. It's going to give you a vector that goes along the direction of X, and it gives you one of the vectors of the tangent plane. And UB is dy x dy y dy f x y. Now that's a vector, and you have to evaluate it at the point, because we are looking at the tangent plane at the point Pij. And this is gonna be 0, 1, f, y, x, i, j, right? So this will give you a vector here and another vector here. I'm gonna call it u, not necessarily b. It's gonna give you a vector. It has the same direction as b, but it's gonna give you another vector ub, and then it's gonna give you here another vector ua, right? But the point is, these two vectors, they will give you the tangent plane, right? If you start from Pij and you go, you define the plane with these two vectors, then that is the plane. But we're not looking for the plane, we're looking for the vector A. So what is the vector A? The vector A is the vector you obtain by subtracting the value of this point here on the plane minus the point Pij. So now you have also to remember what is the meaning of this fx and this fy. So I'm going to tell you why here, but you're supposed to know this. So A is equal to delta x times 1, 0, fx, right? And b is equal to delta y 0, 1, fy x, right? Here I'm going to explain why is this true. Okay, so what is the best way to do this? Let me do what I did the last time. Oh, bye bye. Okay, so because in reality, just do it for, let us do it for y, for when you fix y. Okay, so let us fix y. Okay, fix y. So here I'm gonna take this thing here. I'm gonna project it on the XYZ, XZ plane. Okay, the XZ plane. Okay, so we're looking to find this vector here, A, right? And this is our point, and this is our point, and this is delta X, right? And here Y is fixed, is some Y is fixed. We're moving on this direction here, right? So what happens is actually when you take the directional derivative, it gives you the, remember, the directional derivative is actually just the tangent plane, the tangent line of a section of the surface, right? So the surface looks like here, when you fix y, the surface looks like a curve, right? So when you take the directional derivative, it gives you the tangent of this plane here, right? It's a kind of, right? The tangent of this angle here, alpha. So, but then we computed this vector here, UA, right? But we are looking for the vector A. So what you do is just you have to rescale A by delta X. And yeah, because this one, because fx is just the tangent of this vector of this angle here. So it's this over this. When you multiply by delta x, it gives you this length here. Okay, so this is alpha. So think about fx as that's exactly the same as in one dimensional. It's the tangent of this vector here, just of alpha. So when you multiply by delta x, it gives you sorry, I just have to make sure that I'm making sense. So this is or this when you multiply by fx times this times this. It gives you, yeah. Yeah, you have to make sure that everything makes fine, but it's not necessarily this vector here. Yeah. Yeah, because if you have a tangent, if I have a vector, if I have a curve, and you have the tangent here, it's just the value of tangent of this value, right? So it's it's of this. So when you multiply by delta x, it gives you this. Yeah. Yeah. So you just have to make sure that. Okay, so this is gonna be something like that, and the section will be some curve, right? Some curve. Some function here. Then you're gonna have the tangent directional derivative, which will be the tangent line, and then you will have alpha here. So here it'll be so when you take tangent, which is this divided by delta x, right? Multiply by delta x, it will give you this length here, and then on the x-axis, it's just gonna be delta x. So this is delta x, and this will be delta x times fx, right? Okay, and that's exactly what I have here. So I'll encourage you to think about it more, but that's the reason. So here, so these are the elements you have to understand. Now, obviously, you need to spend a bit more time to understand this if you don't, but this is what you need. So you fix y, it gives you a curve, a one-dimensional function, and then you have to remember what it means, the directional derivative of a one-dimensional function, which is a tangent of some. It's a slope of a line, which is basically the tangent of this angle. Then we multiply by delta x because we are moving from here to here, which is delta x. So it gives the z component, and then the x component is given by delta x, which is exactly what I have here. And then you do the same thing for y. It's exactly the same thing, but you have to move on the other direction. Okay, so here, that's exactly what you need to know if you want to understand this formula here, right? So the area of delta t g. So remember, now we have an explicit formula for a and b, right? So these are a and b. Now, what is the area of a rectangle oriented by a and b? That's the a times b cross product. Again, I'm not gonna remember or recall the definitions. You must know this. This is given by the norm of this vector here. Okay. So what is the vector A? Remember, it's delta x 0 because it has no y component, right? We are on the zx plane, and here it's delta. I think it's better if I just so here it's a b, right? So this is the norm of this vector here. Delta x 0, delta x f x xi yj 0, delta y fy xi yj. Okay, which is the norm of the vector minus fx evaluated at the point xi yj, delta x delta y I minus f y evaluated at the point xi yj times delta x delta y k, sorry, this is j, plus delta x delta y k norm. Okay, well, this is what is the norm of a vector with 3 components? This is the square root of this one squared plus this one squared plus this one, but then you have this one which is redundant in all of them. So we take it out, which is delta x delta y, with the square root of this. Now we have to take the square root, which is f x squared evaluated at the point xij plus f y squared plus 1. Okay. Okay. So now we have a formula for the area of this. Right? This is a very explicit formula. It's not the same as before. We have a very explicit formula that depends on I and j. So the area of the surface. So remember, we took this, we summed all of these very small rectangles, and this was the area. Now we have a very explicit formula. Is the limit when n and m goes to infinity of this sum, okay, square root of 1, same thing here, plus f y square root times delta x delta y. So remember, the definition of a double integral, that's exactly the same thing. We just have another function here. It's always the same thing. We'll have delta x delta y and something here. You remember, it was also for the applications. We have like a density here, or a moment or something. But as soon as you have this kind of forms, like you have a point times delta x, you have a point delta x xi, yj, a function that is evaluated on that point, times the small rectangle, and then you sum. That is a double integral. So when you go to the limit, it gives you the double integral over the rectangle. Did I call it R or D? D. But obviously, we're not going to do the same work for general region. It's the same thing. You just have to divide and type 1, type 2, then Fubini. Well, this is D of the function. So what is the function here? It's 1 plus fx squared oh, sorry. Now we're no longer dividing. It's better maybe if I keep doing it like the same line to not confuse you. So that's the area. So, right? Other notations. They call z equal to fx y, and this will be the integral over d 1 plus d x z. This is not the second derivative, is everything, right? Right? So that's the formula. And obviously, you're not going to be asked to do the same work again and again. That is not the goal of this class. Is not to make you do this IJs and do these hard things. You will have to use this formula. Don't redo what I'm doing. For example, you need to learn how to use it. That's not how to prove it, although it's good to know how to prove it. Find the area of the paraboloid. The paraboloid y equal to x squared plus z squared cut off by the plane okay. So so we have this. So this is y, this is x, and this is y, this is z. So it's a kind of reverse parabola with one you're used to. So it's gonna be kind of a lot of parabolas. Okay. Okay, and then you have the plane. Right, that's the plane. Y, this is 25. And then you need to compute the surface of this. but obviously not the top, not the lid. Also, what do you do? So you have to find the region D. As is always the case, you have to find the region D. And the region D is always given by when you have to project somewhere. Here, it's possible to project on the XY, but it's going to be a bit hard. You can do it on XY, and then it's possible. You can project on X, but you will have a parabola on the XY, right? When you project, right? You will have a little tent here, and then you have to multiply by 2 because you need. But you have to always choose the easier one. And it's a good exercise if you wanna try to do it on the other side. That's a good exercise. Try to project on the XY plane, but do it just on the top because it's gonna be the same area on the bottom side. But then you will have to integrate, and then you have to isolate Z, which is gonna give you a square root of something. And then you will have to have a boundary of the integration that are not nice either. You have to isolate also when y is equal to, right? When z is equal to 1, z is equal to 0. So you have to take x between square root of minus y and, but you have to do it. But here is an easier one. When you project on xz, it's much easier. The reason is this. When you project on xz, you will have this circle here, exactly the same circle. I need to, you have the exact same circle. Oh. Right, the exact same circle. Sorry, it's not this, it's exactly the same one, but it's just me. Just me. It's exactly the same circle. Let me try to do a better one. Okay, it's exactly the same circle, so it's okay. So that's the circle. And this is the region V. And so what is this circle here? It's when y is equal to 25. So it's x squared plus z squared equal to 25. Same thing. So the region D, and we have the parabola width that is just above the region D. So it makes, so now we're gonna apply the formula of AS is the integral over D of 1 plus fx squared dy. Okay. which is equal to, so what is less equal, sorry, can you please okay, because 25 is the circle, but it's also the inside of the region we were talking about. Okay, so that's, so what is fx? It's, but now you have to be careful because now it's y plays the role of z. That's a catch. That's a catch because now it's exact. That's a very catch. I mean, we are now talking about a surface area given by y as a function of x and z. It's the same thing as what we did, but z is a function of x and y. Please let me know if this is fixed. This might be confuse some people. That's a very important thing. If you were doing the projection on x and y, you would isolate z. And then you would do what we did. But now it's y, the surface area is given as I mean, it depends on how you describe the area, right? If you, now y is a function of z and x. That's exactly the same thing as, that's why we did here dz, dx, dz, dy. It's it's whatever you're however you're describing the area. Z is just how you describe the image of the points on your domain D. Right? So now your domain D is described as Z and X. Oh, sorry. Sorry about that. Okay. So is this clear for everyone? Please let me know if it's not clear. It depends on how you describe your surface. Your surface is the image of a point on your domain. And if your domain is described as X and Z, so now it's Y. So that is very important to keep in mind. So it's the function is this. So it's dx. So what is f? Right? Now it's x squared plus z squared. Right? So it's 2x. And now fz, not fy. It's d dz it's 2z, right? And now that's why I wanted to include this example. It's to confuse you a little bit so that you understand the concept. It's not just formulas that you have to, it's not like, okay, I'm gonna apply the formula and then that's it. You have to understand what you're doing. It's not like, okay, take Z, apply the formula and compute. No, because you need to understand what is D, you need to understand what you're doing. So Z, why did we use Z, X, Y? It's because we wanted to describe the surface area as a function of X and Y. Now you can do the same exact thing, the same exact analysis that we did, but using Y as a function of Z and X, which is gonna give you a surface, same thing, right? So now you have to use the formula, but using x, z, x will play the role of, y will play the role of z, z will play the role of y, and x will play the role of x. So the surface area is the integral over the region D, square root of 1 plus, did I use this here? Yeah. 4x squared plus 4z squared dA, right? Now it's a double integral as you've been doing lately. Now you can even remove this one and say this. So that's the region. Okay, so now you can do this using x and y, but then you have to, better way to do this is to do polar coordinates. So you put x is equal to r cos theta, y equal to r, you see? So now z plays the role of y, z r sine theta, right? Because then you're just on the x plane, on the xz plane, and the same thing applies. You're just applying, describing a point xz, within theta and the length r, right? Same thing. So as will be the integral over 1 plus 4 r squared cos theta squared plus sine theta squared r squared. Now this is dx dy, right? Now I'm gonna have d theta, right? So everyone is following me here, or did I miss something? No, I missed something, because remember, it's r d theta d theta when you change the variables. Okay. And now what is now the region here? Let me do it. Okay, so that was our region D. Okay, can you go back for it? Yeah. Please let me know when you finish looking so I can move forward. Yeah, sorry, maybe that was a little bit fast. Yeah, thank you. It's 2x squared, 2z squared, right? Remember we're doing this squared, right? And I computed fx, which gave me this, and then I computed fz, which gave me this, and then I put it here. Okay, done. All right. Now I have the region D, x squared plus z squared is less than 25. I can compute the integral. It's going to take me much more time if I do it with xy, but with the region. So now I have my theta, right? Then it's going to swap the region. That's a very simple, that's the simplest region in polar coordinate is a disk. So R is allowed to be from 0 So when you fix theta, it goes from 0 to 5 all along the way. It does not depend on 5. And see, so it does not depend on theta. So each time you fix theta, it goes from 0 to 5. And now theta is allowed to rotate from 0 to 2 pi. And that is our region, which will be the integral 0 to 5, 1 plus 4 r squared r dr d theta. And you know how to do this. This is a very like, this is a one variable function, right? And then it's 2 pi, because this, whenever you have something that does not depend on theta, you can just pull out theta, which will be the 0 to pi. If you have seen this in the book or something, this is why they do this, because it does not depend. I mean, this is a number that does not depend on theta, right? So you can just pull it out, and it's gonna be the integral of 5 r 1 plus 4 r squared, right? Which will be 2 theta 2 pi times 1 over 12 1 plus 4 r squared 3, right? Yeah, that's the calculation you have to do between 5 and 0. And yeah, because it's 4 times 2, 4, yeah, it works. And this will give you, I don't know how much, whatever this will give you, pi over 6, I think 10 square root of 10, right? Or 101? Yeah, 101 minus 1. All right. Okay. Whew. So just make sure it doesn't give you something negative. It's a surface area when the function is positive, like here. It's y equal to. Okay, so that's basically the idea. You have to find the region D, and that's a good exercise actually if you want to do it. Try to do it, but project on X and Y. That's a very good example. It will help you understand everything. Try to do the same example with X and Y. You project on X and Y, isolate Z, integrate from here to here. That's a good exercise. And make sure it gives you the same answer and see which one is easier. But then you have to, as I said, you have to isolate Z, and then you have to use the formula here as I gave it to you. dz dx dz dy. Oh, sorry, here it's, oh, sorry. Dx, oh, yeah, it's a function of, sorry about that. Yeah, see, it's a function of x and z, x and z. Okay. Yeah, please make sure you understand this. Okay, so we'll take a break, and we'll be back at 12:30, and we'll do the change of variables. And yeah, unfortunately, it's moving very fast because I would like to do more examples, but it's a bit moving a bit fast. So what I try to do is I'll try to find some good exercises to put um, on, uh, on the problem list so that you can understand. But remember that you have to do the exercises on your own from the book, and you do have the solution manual, I guess. That's a good thing to do, because you really need to do examples. Yeah, and I will keep doing because sometimes the book has good examples, so I'll take those or modify them. But sometimes I will choose other examples that are not in the book or the exercises. But basically, this book is good because it has a lot of good examples. So there isn't that many creativity you can have when teaching this. Okay, so next half an hour, right? It's gonna be a bit hard to do it in half an hour. We'll talk about change of variables, uh, and that's actually a very nice thing. You will see there is an exercise, and I just included it this week. You will see how double integrals and change of variable will allow you to compute the value of a series that has a very historical meaning. And this is actually a cool thing. This change of variable in 2 dimensions. You have to transform rectangles and all of that. And then hopefully we'll go to vector calculus, which is also another cool subject. Okay, so let us be back at 12:20. And sorry if it's too fast.
Okay, welcome back everyone. Let's do now the change of variables. So again, this will be a bit more technical to prove these things. But the point is not to prove things. The point is to make you understand why they work. Because if you want to prove these things, it's gonna be much more longer to do this and harder. Yeah. So change of variables. Okay, so you are familiar with the change of variables in one-dimensional, uh, one variable change, change of variables. Change of variables in 1D. So remember what happened. Yeah, you used to have a function. You integrate from A to B, function fx dx. And the change of variable allowed you sometimes to compute this. What you do is you find a function, x is a function of y, of u, and then c, d, and then you integrate with respect to u, right? But there is something that goes in here, which is du dx, right? Remember this one. Dx du. Dx du, right? And then you integrate from C to D, where you have G of C is equal to A, and then G of D is equal to B, right? Yeah, thank you. So now we would like to know what is the analog of this change of variable in 2D, right? So it is gonna be a bit more complicated than this, because in 1D, you are transforming one interval into another one. There isn't that much. A linear transform, a continuous transformation of a segment is gonna change the endpoint. That's the only thing that's gonna happen. Uh, that's basically what you're doing. You're taking a line AB and you're just transforming it into another region of integration from C to D of another function. And it depends on you. In 2D, you can have much more complicated than that. You can have a region D, then when you transform, it's going to be something else, something D, right? So that's exactly what happens. So we're going to start by talking a little bit about transformations in 2D, and then that will allow us to speak about change of variables. So this is a discussion that is going to take, I guess, the whole half an hour. I don't know. I'm trying to move to the end, but I will not. I will not just, you know, I don't want to just move very fast and just confuse you. I will go slowly, relatively slowly. I will catch up tomorrow, hopefully, because the two vector calculus is not
At least the two sections are not that much complicated. Okay, so let's suppose you have a region in 2D. Okay, so here pay attention because we're gonna move backward. It's gonna be a bit confusing in the beginning, but don't be confused. We're gonna move backward. You can like you will have questions. Why are we doing this? Why are we doing it in that way? But the reason is because I know the answer, because I know it's gonna make sense by the end. But if we just go with your intuition, it's gonna be messy by the end. So that happens a lot in mathematics actually. So suppose you have a region R, right? And you will understand what I'm saying right now. Right? Suppose you have a region R in the X and Y plane, right? So what's the goal? What's the goal? The goal is I give you a region R in the XY plane, and it's too complicated to do the integral. So we need to do something else to compute the integral. So the thing to do is not to transform R. That's what I'm talking about. It's not to transform R into another region. The right thing to do is to look for a region in the UV plane such that when it's transformed, it gives you R. That's the catch, right? So that's what I'm gonna talk about, transformations, T. We are in the UV plane, right? You have a point. And again, why we're using UV instead of XY? It's because we don't want to confuse you, because basically these two are living in the same space. You are in R2 and you have a circle and R, you apply you deform R, you deform the circle and continuously it's going to give you another thing. You do live in the same space, R2, but we are doing calculus. So if you're not in calculus, if you're not changing the variables depending on your situation, you're gonna get confused. You will not know what is X and Y, because if you choose X and Y instead of UV, it's gonna be a complete mess. So that's why we parameterize things using different variables. That's why. Okay, so we have a region. It's this. The idea is this: you want to describe something. How you want to describe it? Well, in some cases, you're gonna describe it X, Y. In some other cases, don't choose X, Y. You can choose Y, L. You can choose whatever you want. Well, you're gonna choose UV, just to stick with the book and not confuse you. Okay, so suppose I have a region here, call it S. And then it applies some kind of deformation, it gives me R. Well, this is what it's called a transformation, right? So mathematically speaking, what it does, that this is the intuitively speaking. Now, what mathematically speaking, it's I apply T to a point, and this point is transformed to another point, X and Y. Now I'm gonna say, okay, I'm gonna choose U0. Okay, I'm gonna choose X and Y. But don't get confused with X here and X here. It's maybe it's better to. This is the Y. This is the Y axis. This is the X axis. Right, UV axis. This is the V axis. Okay. And so you choose the point UV, transform. So mathematically speaking, it's this. It's T. You apply T to UV, it'll give you a point XY, XY. So the idea or the goal is to find a simpler region S such that T of S is R. Right? We'll have to do more work, but the idea is this. You want to integrate over R, Suppose you have an integral. Suppose you have another region. It's a circle, or something very simpler, like a rectangle or something. So instead of integrating over R, I can integrate over the simpler region. But there will be something that is going to come up when you want to. Yeah, you have to pay a price, right? The price here is going to be called the Jacobian. It's instead of, it's going to play the role of this function here. Like if you want to integrate a function on a something here, you can integrate on a simpler domain, but you have to pay the price. The price is this thing that is going to come up here, and it's going to complicate sometimes the function, but it's either one way or the other. That happens a lot in mathematics. Yeah, it's simpler, but you have a much complicated function that is going to come up, but that's the best you can do. But as you'll see, like in a lot of cases, the price will not be that high. Okay, okay. So let's do this in a bit more details. So what does this transformation gives? Explicitly speaking, mathematically speaking, what it gives, it's always given by some kind of these transformations are given by T is given by X will be a function of UV, and at Y is a function of HUV, right? It makes sense, right? Because what is the point X, Y? It depends on U and V, right? I mean, the point X here is the image of this point, which depends on the point, which depends on U and V, right? So X and Y, they are both function of Y and V, right? So what is the image of the point UV? It's this, right? So the image, so if I give you the point UV and I ask you what is the image is just G UV H UV, which is X and Y. Okay? And we'll assume that in general G and H are C1 functions. Well, C1 function, this is a very, very technical thing. We're not even gonna use it anyway. It's used in the proof, the formal proof, because you want also what C1 means is the first derivatives are first order derivative. But don't worry too much about this. It's really a technical thing. Derivatives are continuous, because at some point in the proof you will get are continuous. You will need that these things are bounded, or so you need them to be continuous. Okay, so okay, so there's some technical things here. Point here, x1 is called the image. Of UV, U1, V1. Okay, T is called one-to-one if 2 points have different images. well, no, maybe that's not the same. That's not the right way to say it. If no 2 points have the same image. Okay. Everyone is following me? Derivatives. Yeah, derivatives. Is everyone is following? So whenever I have a one-to-one, one-to-one means that you cannot have 2 points giving you the same point. That is not going to happen. And when you apply t, it's not going to give you the same point. That is bad. Whenever you have a 1-to-1 correspond transformation, t process, is this the right way? Okay. Process and an inverse. Okay. Which means that because if you 2 points, they give you the same point, you cannot check the inverse of a point because suppose this happens. So what is the inverse of, suppose this is x0 and y0, and this is u1 and v1, and this is u2, v2, right? What's the inverse of x0, y0? It's not defined. It's not really defined. But when this does not happen, you can have an inverse function. It's well defined. And the thing with this inverse is if you apply something, right, and then you go back, it's this. So that's the inverse. It does not always exist, but it exists sometimes. Okay, I think I need to do an example because this is gonna be very, very abstract for some people. Okay, so for example, take the following transformation. Consider the following transformation. T uv is 2u plus 2u, 3v, and then u minus v. Okay, which is x and y. Okay, now let's take the following region in the UV plane. Okay, this is the region S. You have 3, you have 2, right? Okay. And then we'll call this one S1. Okay, S1. We'll call this one S2. We'll call this one S3. And we'll call this one S4. Okay, is it 2 in the U-axis? Yeah, it's 2. It's 3 on the U-axis. This is 3. This is 3, this is 2, and this is V-axis, and this is the U-axis. Okay, so now when you transform this, right? This is the X, and this is the Y-axis. So now the question, what is this? Now we're moving forward. We're applying T to S, right? Before I asked you, right? Because in general, we have to find S. But now it's just to explain to you what happens when you apply. In general, you have to find S such that, but now it's just, okay. So what is T? So now you have to apply T to each boundary. That's the thing with this. You always do it. You take S, you take the boundaries, because it's a continuous. It's gonna be this. The case is we'll always be dealing with continuous transformations. We'll take boundaries to boundaries. It's not always the case when the function is not continuous. It can blow up some region into some unbounded region, and it's not gonna, some weird things can happen. But in continuous functions with a C1 functions, they're bounded. And if S is bounded, then the image will always be something nice. If the original region is nice, which is a square. So here, so now we're gonna investigate what is the image. So now we apply it to S. We need to find the image. So we need to find the image of the boundary of S. Okay, so now let's do for S1. Okay, for S1. So what is S1? So S1 is U is between 0 and 3, and V is equal to 0, right? So that's U. So T of S1 is, so now we apply. X is T of U, all right? Remember this is T, right? Remember T of U, it's 2U plus 3V, U minus V, right? So if I am on the region U between 0 and 3 and V is equal to 0, X will be, this is X and this is Y. So V is equal to 0, so it's 2U plus 0V, which is 2U, and Y will be U minus 0, will be U. So what now they are parameterized using U as a variable between U and between 0 and 3, and U between 0 and 3. Now this is nice, but you want to look at what they look like in the XY axis. So you have to express X as a function of Y. So you do this by getting rid of U, right? You have to get rid of U. In this case, it's easy. You just U is equal to Y. So X is 2Y. right? Because I'm just using u here, right? So, and x is between, okay, so if u is between 0 and 3, 2u is between 0 and 6. So that's a line, right? So now I'm gonna remove this, and then I'm gonna use another color, the same color. So this one is the line that is from 0 to 6, and it's something like that. Right, so this is t of S1, and this will be 6, because x is between 0 and 6. Okay? Maybe I should do a better diagram here. Maybe I should do a better, yeah. So this will be 6, and this is t of S1. Okay, now you do the same exact thing for S2. For S2. So what is S2? Remember, S2 now is this line here, this vertical line that has a fixed x. For S2, it's u equal to 3. I should have used the blue one here, but it's fine. And v is between 0 and 2. So t of SU, now you use the same formula. Formula says x is equal to 2u plus, it's 2u plus 3v. But now u is fixed, which is equal to 3, which is 2 times 3 plus 3v. V is a variable, so it's 6 plus 3v. And y is u minus v. Well, now u is fixed, it's 3 minus v. And v is between 0 and 2, right? So now I have x and I have y, and they are both expressed in v. Now we have to isolate v, right? Now, so x is equal to 6 plus 3. Now v is equal to 3 minus y, right? I'm using this one here, which is equal to 15 minus 3y. And now, what is the range of x? You have to express everything in terms of x and y. Now, if v is allowed to move from 0 to 2, and x is equal to 6 plus 3v, so what's the range of x? You just have to, this one is, this 3v is from 0 to 6, so 3v plus 6 is from 0 to 12. Now you have x, this, so now I have to plot this along with TS1. So of course they're gonna match, right, on their endpoint. So now it's a linear, it's a line that starts at 6 when x is like, you have to isolate y, right? Y is equal to 15 minus x over 3. So of course, sorry, did I make a mistake? No, sorry, this is 6. So when it's 6, it's 12, it's 3. So y is equal to 1, right? 6, 12, 3, so it's y is equal to 1, sorry. Okay. 3. When it's 6 is 12. Okay. Yeah, it's 3, so they match. Okay, now it's, and this is 3. Okay, so this is T of S2. Okay, we're running out of time, but you get the idea, right? So now you have to do the same thing for, it's the exact same thing, right? You have to put S3 and S4. So for S3, do it. It'll give you, this. For S3, it'll give you the line here, right? This is gonna be T of S3. And then for the last one, S4, it'll give you the line here. And then of course you have to move in the direction of, do not be confused. Like this one is in this direction, and this one we are moving in this direction, and this, and then it'll be in this direction here, and then, right? Because we moved from here, right? Right, because 0 from X was from 0 to 3, and then V was from 0 to 3. So we move along these directions. So that will be the result. And then this is not done in the book, but you will always need to at least um, find a point here at any point. This is not done in the book, but they should do it. You should at least give an argument why this region here. There are two ways you can do this. One is conceptual, and the other one you can do it computational way. I mean, this region here, when you map the boundary, it gives you, but there is no guarantee that it's going to be the inside. It can be the outside with boundary, right? Well, the reason is because a continuous transformation will map a bounded region to a bounded region. So it cannot be the outside, right? It cannot be really the outside because there is no reason to believe that it's the inside. Yeah, you just what we just did here is we looked at the image of the boundary. There is the image of the boundary, but what happens to the interior? There are two ways you can do this. Either you say, I have a bounded region, so it needs to be a bounded region. So there is no way to be the outside region. So it has to be this one. Or the other way is you take a point, right? And this is required. You need to do this. Take a point inside anyone and just make sure that it's inside. It's somewhere inside. Take a point here and then just show that it's the image of this point. For example, take the center or something just anywhere here and prove that it's inside. And that's gonna be not a proof, but at least we are sure that the inside is mapped to the inside, right? So you want to make sure that the inside is here. So if you take a point in the inside here, and you make sure that it's inside, and that's okay. That's a kind of argument. We'll call it a semi argument that it's the interior. But in the book they just say, okay, it's the inside. But you don't have to go that deep. But again, the real reason is it cannot be the outside because the outside is an unbounded region, and continuous transformation will never map a bounded region to an unbounded region. That's the reason. So this is T of F. This is T This is T of S. Okay. So yeah, I'm gonna stop here. But here's the thing. Suppose you have to integrate over this region here, TSR, in the XY plane. This is the XY plane. So that's, so and then you found this transformation T that gives you this region here, right? It's a simpler region. So instead of doing this complicated integral, you will have to do this very simple integral, just from 0 to 3 and then 7 to 1. Then, as I said, we're gonna do this tomorrow, but you're not gonna integrate exactly the same function. You're gonna integrate the same function up to a Jacobian, which will be another function that's gonna multiply the function. Okay. Okay, so hopefully that was clear enough. Make sure that you do some exercises and read the examples from the book. There are other examples that you can read. Can you scroll down a bit? Down, okay. So there are other examples you can read in the book and do some exercises. And we'll make sure that we include in the problem list some issues that make you understand better these concepts. Yeah. Okay. So I'll see you tomorrow, guys. All right. Thank you. So everyone is done? I can remove the sharing screen. Okay, I'm gonna stop sharing my screen right now. Stop sharing. And then, bye-bye.